Caroline, thanks for your question. This is a great question. We're given a piecewise function and they ask us to determine continuity of the function at the values x equals 2, 3, and 4. And then they ask us to graph the function. So to determine continuity for this particular function, we actually need to look at the technical definition, which is that if g of x is continuous, the limit as we approach from the left will be the same as if we approached from the right, will be the same as if we just evaluated the function. So let's look at the first number, x equals 2. So we're going to look at the limit of g of x as x approaches 2 from the left. We need to be careful in considering which piece of the function we pick. If x is approaching 2 from the left, we're looking at all values less than 2. So we're going to go ahead and pick this top function here, and we'll plug it into our limit. And if we do that, we see we can just pop 2 right into this function here, and we'll end up with negative 4 plus 4, so we'll end up with 0. Now let's look at the limit as x approaches 2 from the right. As x approaches 2 from the right, I'm actually at the second piece of the function. So I'm going to plug in the second piece. I can plug 2 into this function here, and I'll just end up with negative 2 plus 2 is equal to 0. So these two limits are the same. Now let's go ahead and evaluate the function at 2. So if I look at the place where g of x can equal 2, this is actually the first function again. So if we plug 2 back into the first piece of this function, we'll end up with 0 again. So all of these are equal at x equals 2, which means the function is continuous at x equals 2, so it's continuous at the number. Now let's go ahead and look at x equals 3. We're going to go through the same process. As x approaches 3 from the left, we're looking at values that are less than 3, so we'll be looking at the second piece of the function. If I plug in 3 here, I get negative 3 plus 2, so I get negative 1. Let's go ahead and look at as we approach 3 from the right. I'm looking at all values greater than 3, so I'm looking at the third piece of the function. If I plug in 3 here, I still get negative 1. Now let's go ahead and evaluate the function at 3. If I pick the piece where g is allowed to equal 3, I get the second piece again. So we can say that g of 3 is equal to negative 3 plus 2 is equal to negative 1. These are all equal. So at x equals 3, we are continuous at the number again. Sorry about the terrible handwriting there. Now let's go ahead and look at x equals 4. So we're going to go through the same process again and look at the limit as x approaches 4 from the left. As x approaches 4 from the left, I'm looking at all values of x that are less than 4. So I'm going to plug in the third piece of the function. If I do that, I can see that I end up with 0. If I look at the limit as x approaches 4 from the right, I'm looking at all values of x greater than 4. If x is greater than 4, I can see I just end up with pi here. And if I look at the piece of the function where x is allowed to equal 4, I also end up with pi. So I can see what I have here is that My limit as x approaches 4 from the right is equal to f evaluated at 4, but my limit as x approaches 4 from the left is not equal to my function evaluated at 4. So in this particular case, g of x would be, I'm sorry, that should be a g. G of x would be continuous from the right. Okay, now let's go ahead and look at the graph of this function. For the graph of this function, I'm going to go ahead and look at the pieces where the function is split up. It looks like we start at x equals 0. So I'm going to go ahead and put a closed dot at x equals 0. And then my function continues over to x equals 2, and it is allowed to equal 2. So I'm going to put another closed dot at x equals 2. In between x equals 0 and x equals 2, I have a downward facing parabola. So we'll just sketch a little downward facing parabola from x equals 0 to x equals 2. Let's go ahead and look at the next piece of our function. This goes from x is greater than 2. So I'm going to start there, and then I'm going to x equals 3. So I'm going to put a closed dot at x equals 3 at the place where my function stops. Let's figure out what it looks like from x equals 2 to x equals 3. It looks like I have a line with a slope of -1. So starting at x equals 2 and ending at x equals 3, I'm going to draw a line with a slope of -1, and we will put a closed dot here. That should be a straight line right there. Let's go ahead and look at the next piece of our function. On this piece, I have a line with a slope of +1. I'm starting at x equals 3 and going to x equals 4, but at 4, I am not allowed to let my function equal 4 for this piece. So we're going to start at x equals 3, draw a line with a slope of +1, but our function is not allowed to, our function does not exist there. So we have an open dot. Let's go to the next piece of our function. Looks like for all x is greater than or equal to 4, our function is just a constant, which is pi, so approximately 3.14. So at x equals 4, I'm going to jump up to approximately 3.14. My function is allowed to equal 4 here, and it's just going to be a straight line from here on. And you can see that this reflects the continuity of the function that we determined earlier in part A. So this would be the final answers for your problem. Thanks again for your question, Caroline, and I look forward to answering more of your questions using SnapMath in the future.